welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 16 physics series, where we are discussing each and every chapter so that you can achieve the dream of 60 in your upcoming KCET 2025 exam in physics. And today we are going to complete the chapter Dual Nature of Radiation and Matter. We have already completed 50% of the chapter in part 1. If you have missed that part, you can go back to our channel, you can go to the playlist and check the video. And today mainly we are going to discuss about photoelectric effect and wave theory of light. So photoelectric effect is based on basically the Einstein's equation, and then wave theory of light, de Broglie equation, etc, etc. But before that, tomorrow is Sunday and there will be a KPL mock test 6. So KPL mock test is happening tomorrow, and for that what you have to do, you have to join our WhatsApp channel. The link is given in the description. First go there, join our channel, click on the bell icon so that you get the notification as soon as the question paper is posted. So tomorrow we will be posting physics, chemistry, so don't forget to download the question paper, solve them, and then at night when I am coming back with the solution, check how much marks you are getting from that part. So now let's start with today's topic. All the topics that we are going to cover. First of all, we will start with Einstein's photoelectric equation. We have already covered all the experimental observation from photoelectric equation and how this can be explained, that we are going to discuss. Okay, why this is some weird thing is happening, why there is a some work function is there, why there is a minimum frequency is there, everything will be explained today. Then we will discuss about work function. Obviously work function, we have discussed what is work function, but how it is affecting the Einstein's equation, that we will discuss. Then we will discuss stopping potential as well, everything about stopping potential. If you remember the experimental setup, if you apply a voltage opposite to that of the flow of electron, then some electrons are not coming out, so minimum potential is there, so that we are calling at stopping potential. Then particle nature of photon, that also we are going to discuss today. Then we will discuss wave nature of matter. So everything will be completed today. The chapter will be completed. Day after tomorrow, that is Monday, I will discuss all the PYQs from this chapter. Now in this week's KPL that is happening tomorrow, we are not giving this chapter, only ray optics and wave optics. Ray optics full chapter, wave optics full chapter is there for tomorrow's KPL. This topic, this chapter will be there in your next week's KPL. So don't worry. So since I have not completed the PIQs, I have not included this chapter for this week's KPL. This week only ray optics and wave optics will be there. So practice them, these two chapters, and attempt the question paper tomorrow. Now let's move on. First discuss Einstein's photoelectric equation. So photoelectric emission does not take place by continuous absorption of radiation. So what is the meaning of that? For example, if we have, suppose we have some substance, okay, say a metal wire, metal rod, metal plate is there, it is kept in sun, okay, and sunlight is continuously falling on it, right? So as it is absorbing the sunlight, it should get heated up, right? It is getting heated up, but in case of the sunlight, the frequency of sunlight, suppose it is higher, lower than that of the threshold frequency, then you should not get any radiation out of it, no matter how much you keep it in sun. Okay, it does not happen unless and until the frequency of light is more than certain minimum value. So why it is so? This is a very big question regarding this phenomena. So this phenomena was unexplained, even though it was discovered very early, but it was remained unexplained for a very long time, 30-40 years. It was not no one was able to explain it. So why it is so? Basically what is happening here is, we know that some material absorb heat. As soon as it is absorbing heat, the heat should convert into the kinetic energy of the electron, and electron should come out. That was the basic concept that should have happened, but actually this is not happening. So why it is not happening? So Einstein came to the rescue and he said electrons cannot absorb any amount of heat that is given to it. So he said radiation energy is built up of discrete units of so-called quanta of energy of radiation. So quanta means, as we have discussed in electricity chapter, quanta means it has a minimum value. That value needs to be there. Now as far electrons are concerned, electrons minimum value is fixed. Okay, but radiation, when you are talking about radiation, different radiations have different minimum value. Okay, so for example, blue light's minimum value is different from that of the minimum value of red light. Okay, that is very clear, that you have to keep clear in your mind, that even though for the earlier example of quantization where we have studied that there is a fixed minimum value, here because different lights have different wavelengths, different lights have different frequencies, so the minimum value varies from light to light, from color to color. Okay, ultraviolet will have a different value, X-ray will have a different value, similarly infrared ray will have a different value. Okay, so everyone has a different value, but that is called a quantum. So if I am only considering, say, red light, so all the red light will have a fixed definite minimum value. That value is very important. So each quantum of radiant energy has energy h nu. Now you can understand why I said it depends on the frequency. So nu is the frequency of the light. So as you can see, higher the frequency, the higher will be the quantum. Right, so minimum possible value will be higher. So for example, blue will have a higher amount of energy compared to red light, right? Similarly, ultraviolet will have higher energy compared to blue light, right? So as you are going higher in frequency, the minimum possible value is more, right? So this is like the quantum of energy. This is called quantum of energy. Quantum of energy, I gave you one example, that there is a milk packet. If you visit a shop and you ask, I need a half packet of milk, or I need a glass of milk, they will not give you a glass of milk. They will say, I have a packet of milk. You buy a big packet, you buy a small packet, but you have to buy one packet full. I cannot give you, cut it, and I cannot give you half glass of milk, right? So that is not possible in case of you are visiting a milk shop, right? So that is why this is called a quantum. Quantum means the smallest possible value, right? Where h is the Planck's constant and nu is the frequency of light. So as I explained, h is the Planck's constant, it has a fixed value, we will see that value 6.634 times 10 to the power minus 34, okay, in SI unit, and nu is the frequency of light based on what light you are using and what is the frequency of that light. So this value will change, right? Now the maximum kinetic energy of the emitter electron. So when the electron is coming out of the surface, after the radiation is falling, electrons are coming out. So electron will have a kinetic energy. So that we discussed yesterday. So the maximum kinetic energy, the maximum value of the kinetic energy is given by Einstein's photoelectric equation. He said that maximum kinetic energy, K max, is given by h nu minus phi naught. So phi naught is called work function. Work function is the minimum amount of energy required to get one electron out of the surface, right? We have briefly touched it. Today we will see it in a detail. Now let us solve one problem. Light of two different frequencies whose photons have energies 1 electron volt and 2.5 electron. Now in case we are talking electrons, so better to write the energies in terms of electron volt. So now what is electron volt? Electron volt is nothing but 1 electron volt is charge of 1 electron times 1 volt. Okay, so SI in SI unit it is nothing but 1.6 times 10 to the power of minus 19 volts. Okay, or 10 to the power minus 19 joules. Okay, in SI unit it is nothing but 1.6 times 10 to the power minus 19 joules. Now as you can see, this is a very small energy, and for electron this is very sufficiently high energy. So for electrons we generally mention 1 electron volt, 2 electron. This is 1 electron volt. Okay, 2 electron volt means twice of this energy, right? So 2 different photons have energies. We have not yet discussed about photons, but for now assume that they are particles whose energies are 1 electron volt and 2.5 electron volt respectively, successively illuminate a metallic surface whose work function is 0.5 electron volt. Ratio of the maximum speeds of the emitted electrons will be. Now we know that K max equals to energy h nu minus phi naught. Now this 1 electron volt itself is given in a form of energy. So h nu together is given. Okay, 1 electron volt is together the value of h nu. Okay, so h nu is 1 electron volt for the first case, and the work function is given 0.5 electron volt. So it will be 0.5. This is for the first case. Okay. Now for the second case, it is 2.5 minus 0.5, that is 2 electron volt. Now let's find the ratio of that. So what is the ratio? K max 1 divided by K max 2, that is 0.5 divided by 2. So it will be 1 by 4. Right? Now what is K max 1? What is the expression for kinetic energy? Kinetic energy is half m v square, right? Mass for electrons will be same, only the velocity will be different. So half m cancels, so it will be 1 by 4. So V1, they have asked you to find the ratio of V1 by V2. So as you can see, it was V1 square by V2 square. So what we have to do, we have to find the square root. So it is half, that is 1:2. So 1:2 is the correct answer. Simple question. These are not very difficult question. I hope you have learned about this equation. You have studied this equation in your class. If you have not, mention in the comment below, sir, I have not studied at all. So then I will be practicing more and more. Also, if you have not practiced these equations, don't worry. In our next lecture, Monday's lecture, we are solving PYQs from this chapter, where we are doing a lot of questions based on these equations. So there we are solving questions, so don't miss out on any PYQ sessions. Actually, PYQ sessions are more important than actual lecture sessions, because there we are actually by hand we are solving the questions. Okay, so hands-on approach there. So don't miss any PYQ sessions. If you have missed any PYQ sessions, you can go back and watch those PYQ sessions. Now let's move on to the topic of work function. In the equation, work function is given by phi naught equals to h nu naught. Okay, so if you see in the Einstein's equation, we have learned that K max is equals to h nu minus phi naught, right? So now we are saying that phi naught is basically nothing but h nu 0. What is nu 0? This is the minimum energy required to free the electron. So this is the minimum amount of energy required to free the electron, and nu naught is the threshold frequency. If you remember, there is a minimum value of frequency required to release one electron. That is why this is called threshold frequency. Okay, now electrons, let me explain it in briefly why this minimum energy is required. As we know that electrons are orbiting in orbits, right? These orbits are different, and in chemistry you have even learned about orbitals as well. So in physics we are not interested in orbital anytime soon. We will learn about orbits and energy in the orbits in the atomic structure chapter, but for now, let us assume that there are different shells. We have learned K1, K2, right, K3. Okay, and if suppose the electrons are only located up to K2. Okay, so electrons are located up to K2, that means this is the valence shell, right? You have already familiar with these terms, valence shell. So when this electron comes from this shell to this shell, this becomes conducting electrons. They are conducting, they are free, but they are still bound to the metal. But somehow if you can free them to the next level, then they become completely free. Okay, they become completely free of the any bound of the nucleus, right? Now to get this, there is a fixed energy gap. Okay, we have already learned that in chemistry that there is an energy gap between different levels. Okay, this is called excited state, this is called ground state. So different states are there. We will discuss about them briefly in our next chapter as well. So now this energy gap is fixed. Okay, so if you give this electron, suppose this electron requires 2 electron volt to jump from this level to this level. Right? Now what will happen if you give, say, 1 electron volt, but you give 2 photons? Two of the 1 electron volt radiation falls on this charge. Then what will happen? At a time, 1 electron can absorb only 1 radiation. It cannot absorb 2 radiations. Okay, for electrons it is impossible. Electrons are very small, so they cannot absorb more than 1. So one, it absorbs, say, 1 electron volt, it will go up, it will reach somewhere in the middle. Then you will say, okay, I have not been able to reaching there, so what you will do, it will again come back and drop here. So electrons are jumping, but they are not able to reach to the next level. So if they are not able to reaching the next level, they have nowhere else to go. So they will come back and they will sit back at their home. Okay, and again then it will absorb the second photon, and then again it will go to somewhere in the middle, and again it will come back. So it is not possible for the electrons to move if you give the energy less than this 2 electron volt. So if you give the 2 electron volt exactly, then it will just go to the outer surface, and then they will become free and they will just roam around. Okay, if you give it more than 2 electron volt, 2.1 electron volt, then the extra energy that you are giving, that energy will convert it into the kinetic energy of the electron, and it will start moving. So that is the basic fundamental behind this equation. Okay, now let's look into the stopping potential. So we have learned that when electron is out of the metal surface, okay, if you apply a reverse potential so that the electrons are not able to move towards the collector, so you are actually making the collector negatively charged and the emitter positively charged, so that the electrons whichever actually coming out of the emitter, they are going back to the emitter itself. Okay, so that minimum potential required so that the current becomes 0, that is called stopping potential. Now the Einstein photoelectric equation in terms of the stopping potential is given by E V naught. E is the charge of an electron. Okay, V naught is the stopping potential, is equal to h nu plus nu phi naught. So this is the work function, this is the energy given by the photon, and this is the total kinetic energy. Now kinetic energy of any electron can be represented by charge times potential applied, right? This is the charge time potential applied. So I have already discussed that while solving that problem, and usually it is denoted in the units of electron volts. Okay, electron volts, small ev is basically representing the total energy of an electron. Again, using the relation for work function, we can write E V naught equals to h nu plus h nu naught, right? So we can write this equation as h common nu plus nu naught. This is also one way to write. Okay, there is a mistake here. This is not plus sign, this is minus sign, right? So this is minus sign. Okay, so basically this is the formula for Einstein's equation in terms of work function and stopping potential. Okay, so you can calculate stopping potential, you can calculate the work function based on this equation. Now let's solve yesterday's homework problems. I have given 2 homework problems, those are very important, so let's solve them one by one. The maximum kinetic energy of emitted photoelectrons depends on intensity of the radiation. Okay, so basically we are asking the same question. Today also we can answer this question, but let us see that the maximum kinetic energy of emitted photoelectrons depends on intensity of the radiation, frequency of the incident radiation, speed of the radiation, number of photons incident in the rotation. Okay, so we know that from today I can answer this question easily. K max, that is the maximum kinetic energy, okay, is h nu minus phi naught, right? Now, is it dependent on the intensity? It depends only on the frequency of the radiation. It does not depend on the intensity of the radiation. So, maximum kinetic energy is independent of intensity. It only depend on the frequency of incident radiation. I discussed this. There was a point that we discussed that it only maximum frequency depends only on the frequency of the incident radiation. It is independent of the intensity. But the photoelectric current, maximum photocurrent or saturation current, that depends on the intensity. So, saturation current depends on intensity, whereas maximum kinetic energy of the emitted electron depends on the frequency of the radiation. Now, next question. From the following graph of the photocurrent against collector plate potential for two different intensities, light I1 and I2, one can conclude that, so what is the answer? So, there are two intensities of same radiation, okay, same color, same frequency, right? Because you can see that they have same stopping potential. So, same stopping potential means, so if you forgot about stopping potential, that's why this question is good to remember. Same stopping potential means they have the same frequency, right? Stopping potential depends only on the frequency. So, same stopping potential means they should have the same frequency, say nu and nu. But it has higher amount of saturation current compared to this. So, higher amount of saturation current means its intensity should be higher. So, we can say that I2 should be greater than I1. Why? Because it has higher saturation current. Now, from the given option, you can see that correct answer they have not given it is I2 greater than I1, but they have given I1 less than I2. Okay, so I1 less than I2 is should be the correct answer. Comparison is not possible, is incorrect. We can compare easily. Other two options are incorrect. Now, let's move on to the topic next, particle nature of light, that is photon. So, let us discuss in a detail. So, in interaction of radiation with matter, radiation behaves as if it is made up of particles called photons. Okay, so basically why we are calling that? Because electrons, which is a particle, right? So, it is absorbing electrons, it is absorbing whatever radiation energy is falling on it. So, basically you can say that there is a collision happening between radiation and electrons. Okay, so we know that there is, you are playing carom. Okay, if you are playing carom, you are hitting the carom with the striker. So, what is happening? The carom is getting stopped and the striker is stopped and the carom is moving and it is falling on the hole, right? So, that is the playing strategy of carom. Similarly, the photon, which is the radiation, which is basically carrying the energy, it is striking the electron and making it to move, and itself it is coming to a stop, you can say, or it is transferring the energy to the electron and then it is moving, right? Now, that interaction can happen only between particles, right? For example, if you see, if you take a carom and if you put some light onto it, the carom will not move. Okay, but in case of electrons, they are actually interacting with this light. Okay, electrons can interact with light. So, that is why these lights are very tiny. You can consider them to be a very tiny particles which are basically interacting with electrons. Okay, and these tiny particles are called photons. So, photons are basically nothing but tiny particles of light. Okay, so we have started with wave theory of light. Okay, wave theory of light, using this we have able to explain the diffraction, we have able to explain the interference, also we have explained polarization, but for photoelectric effect this wave theory is not applicable. Okay, so wave theory, even though these are very this is a very good theory which is explaining all the other things. Even normal rectilinear propagation of light can also be explained using this wave theory, but this photoelectric effect cannot be explained using this wave theory. So Einstein came up with a new theory, and from that theory we have assumed that the light is basically a particle, okay, a packet of energy. Okay, so this is called photons. Now you will see that we cannot simply ignore wave theory as well. So we have get a new theory. So using that new theory, if you go back and try to explain interference and diffraction and polarization, we will not be able to do it properly. Okay, there will be lot of lacks, lot of gaps, lot of things that we may not be able to explain. So that is why wave theory is valid, and this theory is also valid. So that is why it is called dual nature. Dual nature means sometimes it behaves as wave and sometimes it behaves as a particle, and it depends. It's not sometimes, basically they have, like, you can imagine that it's like a horse, body of a horse and figure of a man. You know, if you are a Harry Potter fan, you know the animal, name the animal in the comment below. So it was one of the analogy given by, not me, someone great, that light is like that. So sometimes you are seeing the human and saying, okay, it is a human. Sometimes you are seeing the lower portion and you are saying the horse, but unfortunately you cannot see both parts because of some limitation. So either you are seeing it is as a horse and you are saying, okay, this is a horse. Sometimes you are seeing the upper face, upper body, and you are saying this is a human, right? So light is like that. Okay, so it sometimes behaves as human, sometimes it behaves like a horse, sometimes it behaves like a wave, sometimes it behaves like a particle. Very interesting, right? So this is a complete, very, very interesting science. Even if you are not interested in physics, even if you are not super interested in physics, these are the stories that should give you enough encouragement so that you get the encouragement to study physics, which sometimes appear to be boring, sometimes appear to be hard, but these are the little bit of smiling. Now each photon has energy E equals to h nu. Right? So that is the energy. So energy of the photon is given by h nu. H is Planck's constant and nu is frequency of the light. And momentum, now as soon as we are calling this as a particle, as soon as we are calling it a particle, what the particle should have? Particle should have a momentum, right? mv. If you remember, momentum was mv. Now for a light particle, okay, particle of light, okay, it does not have any mass, right? So from where its momentum will come? Its momentum will come from its energy. Okay, the momentum of a light particle is the consequence of it is having energy equals to h nu, and its momentum is given by h nu by c. Very important, it is given by h nu by c. H times nu is the energy and c is the speed of light. Okay, so if you divide h nu with c, then you should get the momentum of the light. So whenever you are considering a wave, so you should remember these two things. Whenever you are considering, you are saying this is a wave. So what a wave should have? Wave should have two things. It should have a wavelength and it should have a frequency. Whenever you are saying this is a particle, so the particle should have a momentum, okay, and it should also have a mass. Now photons, which usually does not have a mass, we call it rest mass. There is a little bit complicated thing. We are not going into that deep in this chapter, but if you stop a photon, that means if you stop a radiation for some time, you will measure its mass, you will say, okay, it has no mass, it has zero mass. But when they are moving with the speed of light, they have something called relativistic mass, which we are not going to discuss in this scope, but they also have a mass. Okay, that mass is complicated, not so easy to explain, so I am not going to that detail, but you can still measure its momentum in easier way. If you divide the energy with the speed of light, okay, then you should get the momentum. Because why you get momentum? Momentum is what? Momentum is mass per energy. So from here you can calculate the mass as well. but I am not going into that detail. Okay, now let's move on. All photons of light of a particle of a particular frequency of nu, okay, or a wavelength lambda have the same energy. So all the light particles, I explained that at the beginning, that all the light, suppose I am saying light is blue. Now you take a blue light here, okay, and you take a blue light somewhere in US, same blue light, okay. Blue light has a certain variation, we are not using that. So if you are considering the same variation of light, okay, that is they should have same frequency and same wavelength, no matter where they are. You are doing, say you are testing it in India and you are testing it in USA at completely different circumstances. USA is generally a little bit colder than India, so you are experimenting with it and you measure its energy E1, and the USA scientist, your friend, doing the same experiment in USA measured the energy E2, then they should be equal no matter what, okay. So energy of same frequency and wavelength should have same energy no matter what, no matter where you are doing the testing, no matter how you are doing the testing, they should have the same amount of energy. Very interesting, right? So the energy is same because it depends only on the frequency. Now energy is given by h nu, we know nu is also given by the frequency is given by c by lambda, right? If you remember in your first PU we have learned that V is equal to n lambda or f lambda, whatever you have used that class, okay. What is n? N was the frequency. Now since we have came to second PU, we are no longer using n, we are using a little bit advanced symbol, so that is nu. So nu is now frequency. So frequency, if speed of any wave is equals to frequency times wavelength. So frequency should be given by V by lambda, right? Now for light this V is nothing but speed of light, that is c. So we can write that frequency is nothing but c by lambda. Okay, now this lambda varies from medium to medium, c also varies from medium to medium, but nu remains constant no matter what. That's why these equations are generally written in terms of nu. Okay, so energy of a photon is constant. You should also remember that energy of a photon is constant no matter where it is going, as long as it is not getting absorbed. Okay, so they might ask you the light enters from air to water, what happens to its energy? Decreases, increases, remains same? Not possible to explain. So as long as it is not getting absorbed, see, if the water absorbs some amount of energy, otherwise if it is not getting absorbed, the energy remains constant. In fact, energy of a single photon will remain constant, okay, no matter where it is, because its frequency is constant. Okay, that is the basic thing. Even though the wavelength changes, even though speed changes, frequency is constant. Okay, now momentum is given by hc by lambda, right, h nu by c, so that is h by lambda. Okay, nu by c is lambda, c by nu is lambda, so we can write momentum in terms of lambda. This is the alternative representation of the same thing. hc by lambda is energy and h by lambda is momentum. Okay, now photon energy is independent of the intensity of radiation. So energy of a single photon is independent of the intensity. Okay, intensity is the total energy. Okay, but energy of a single photon will remain constant. It does not matter if you switch on 10 torches, if you switch on one single torch, even if you are using one single beam, the energy of the photon will remain constant. Okay, single photon will remain constant. What else? Photons are electrically neutral and are not deflected by electric and magnetic fields. So photons do not have any electric charges. For example, electrons are negatively charged, protons are positively charged, neutrons are neutral. So photons are also neutral. Okay, and they do not get deflected. That means they do not get induced. They do not get induced any kind of electricity in it. Okay, that is also very important. Okay. In a photon particle collision, okay, so that's what I gave the example where electrons are getting collided with photon. Okay, so as example they have given photon electron collision during photoelectric effect. the total energy and the total momentum are conserved. So momentum, as we have learned the conservation of momentum principle in our first year, so that conservation of momentum is still valid for photon electron collision as well, and the total energy, obviously energy is conserved, so energy should be conserved as well. However, the number of photons may not be conserved in the collision. So number of photons, so suppose one photon is coming and it is colliding with one electron. So electron absorbed the complete photon. So where this the photon goes? Photon is disappeared, photon is vanished, right? But even though the total number of photon is not constant, okay, the energy and momentum should still be constant, okay. Photon numbers can vary from collision to collision based on what is absorbing it, okay. Now the photon may be absorbed or a new photon may be created. Sometimes what happens is that electrons absorb a photon, okay, and partially releases it, okay. So partially releases it means a new photon of new energy it releases, okay. So photons can be created, okay. We will see in our higher classes how can photon be created, but right now we are not going to do the deep analysis of this because this is a little bit higher order physics, so we are not going to discuss that. But for now you can imagine that when an electron moves from lower energy to higher energy, excited energy, it absorbs photon, right? Similarly, when if you give it energy, photon energy, it will go higher to lower ground state to higher excited state, right? Similarly, when it comes back to the lower energy, ground state energy, it gives away the energy, right, in terms of light, and that we are saying the characteristic spectrum of that material. I don't know if you have learned that in chemistry or not. We will discuss this briefly in our next chapter anyway. So you should know that this spectrum is actually creation of photon. This is a destruction of photon. Photons can be created or destroyed, okay, but total energy cannot be created or destroyed. That is very important, okay. Now wave nature of matter. So we have discussed what we are discussing. We are discussing the particle nature or matter nature of light, right? So far what we have discussed, that if a photon, if you consider a photon a particle, then what all will happen. Now what we will discuss is that the wave nature of matter. Very interesting concept, okay. It was pioneered by someone, we will discuss his name as well, and what was his thinking process. When I will give you a small story. He was a student, okay, he was a student and he was more towards studying history, okay. Basically he was doing history major at that point of time when he was discussing this concept with his senior, okay. And his senior said, you know what happened, Einstein discovered this. He said that photon or light radiation is actually behaving like a particle, so that we are observing the photoelectric effect, okay. That point of time this kind of discussions was very common because this was like AI of that point of time. Right now what we are discussing, you know, ChatGPT has solved this difficult problem. ChatGPT is helping us. There was an photographic AI, there is different AIs, right? We discuss AI, different AI discovery every day. So that point of time when these things are coming out, okay, this was a very huge news, big news, okay. Everyone is discussing photoelectric effect, okay, everything will change, okay, we will be able to generate electricity using photoelectric effect, etc, etc, right? That was a big news back then. So his seniors, the person who we will name a few moments later, he was discussing with his friends and seniors, and they said that Einstein discovered that radiation is basically also behaves like a particle, okay. Then he thought, okay, if light is behaving like a particle, why should not a particle behave like a light? That is, a particle should not behave like a wave. So he said that nature was symmetrical and that two physical entities. So he said that nature very much like symmetry. Okay, that's why earth is spherical, not flat. Okay, sun is spherical. Okay, we rotate around a circle. So nature loves symmetry. Symmetry is everywhere in nature. If you see even many, if you take a leaf, okay, for example, natural creation, if you take a leaf and cut it from the middle, you will see they are symmetrical. Okay, so almost all, even we are symmetrical from almost, there are some minor differentiation, but if you see from our, if you consider this line, we are symmetrical, right? We have one hand in this side, one hand this side, one leg this side, one leg this side. So even our organs are somewhat symmetrical, right? We have 2 kidneys, 2 eyes, so okay, so 2 nostrils, so they are also 2 ears. So nature likes symmetry. Symmetry is everywhere in nature. So he said nature was symmetrical, and that the 2 basic physical entities, matter and energy, must have a symmetrical character. So that was his point. If radiation shows dual aspect, so should matter. Very, very interesting, very life-changing line. Okay, this changes the entire science after that. Okay, the birth of quantum mechanics, birth of quantum science, they started from this simple idea. The idea is very simple if you think. Okay, he thought nature likes symmetry, everything is symmetrical. So if light behaves as a particle, okay, which is actually inherently wave, we have found that with Huygens principle, that light actually is a wave which is behaving as a particle in certain circumstances, then particles should also behave like wave in certain circumstances. So what were those? So he said that wavelength of matter and de Broglie wavelength. So the name of the person is de Broglie. Okay, and as you can see, DE is small letter because this is his middle name. Broglie, his surname, the first name I don't remember, but we all call him de Broglie. Okay, so de Broglie, first person, he gave this assumption and he is famous now. Okay, even though at that point, till that point of time, he has nothing to do with physics. Okay, he was a general science student and lenient towards history. Okay, as you have, suppose you are studying in currently you are in studying science, right? So you are studying physics, you are studying chemistry, you are studying mathematics, you are studying languages. So he was a general student, so he was studying all the subjects, but he has a knack towards history. So he thought, I will do my PhD, I will do my research, everything in history. But since this discovery and since he became famous, he switched his career and he became a full-fledged physicist. Okay, so that's how your career, your life, your goal changes. Okay, so this is a very simple thinking. So from there he said, okay, so nature likes symmetry, so that must be it. And he said, if matter, wave behaves like a matter, matter should also behave like a wave. And from there he gave that, okay, what is the momentum of light? Momentum of light is given by P is equal to h by lambda. Right, so P is equal to h by lambda. So what will be the wavelength of the matter? So he said wavelength of the matter should be h by P. Okay, so h by P, h is Planck's constant, P is the momentum. So sometimes this is also written as h by mv for matter wave. This is only for matter wave. Okay, this is valid for both light and matter, but this is for matter wave, particularly matter wave, and this wavelength is called de Broglie's wavelength. Okay, de Broglie's wavelength. As you can see, this depends on the mass, it depends on the speed. Now I am giving you a very interesting task. Suppose your mass is 50 kilograms. Okay, your mass is 50 kilograms. You are moving in a college bus which moves, say, 10 meter per second speed. Okay, calculate your wavelength and then explain why we as a human are not behaving as a wave. Now the implication of this theory is huge. Okay, that means we should also behave like a wave. We should be able to move through matters, etc., like a sci-fi movie, okay, science fiction. So but that is not happening. There is a reason behind that. Okay, you can find it for yourself why we are not behaving as a wave. Okay, now find the de Broglie wavelength for an electron with kinetic energy of 120 electron volt. Okay, so they have given you the kinetic energy as 120 eV. So kinetic energy is 120 eV, and they have asked you to find the de Broglie wavelength. Now what we know that de Broglie wavelength has nothing to do with kinetic energy, but it is h by p, right? So how can we find p from this kinetic energy? There are a few ways. I will give you the derivation so that you can remember it. We know that kinetic energy is nothing but half m v square, right? Now what else we can do? We can write this as m v square is equal to 2ke, okay, or we can multiply mass with both side and we can write 2mke, okay, or mv equals to square root of 2mke. This is the relationship between momentum and kinetic energy. You may have done this derivation while you are studying in first PU, but this derivation was not so much useful in your first PU, but this equation is very useful when you are solving problems, especially in this chapter, okay, especially in this chapter. Now what you have to do, you have to put these values mass of electron is 9.31 into 10 to the power of minus 31. So let me put the values directly, and energy is 120 eV, EV is, so everything is in square root, okay. So and 120 EV, EV is 1.6 times 10 to the power of minus 19, okay. So if you put the values, calculate it, what you will get? Let me see. So 9.31, assume it is as 9 only for now, okay. 9 times 2 is 18, okay, 18. So 18 times 1.6 times 120 times 10 to the power of minus 31 plus 19, very huge number, minus 50, okay. And then we can take this 0 and multiply to this number, okay. So 18 times 16 times 12. So this I am doing to explain it to you. If you are solving it, you don't need to do it like the big way I am doing it. You can solve it in a little bit easier way also. So what we will do, we will take 2 from here and multiply with this number, okay. So it will become 36 and 12 will become 4, 12 will become 6, okay. So it will be 36 means 6 times 16 means 4 times root 6, okay, times 10 to the power of minus 25. So this is the momentum, right? Now what will be the wavelength? Wavelength will be 6.34 times 10 to the power of minus 34 divided by 6 times 4 times square root of 6 times 10 to the power of minus 25, okay. So this is a little longer question, so 6 is almost cancelled, so we get 1 by, what is square root of 6? Square root of 6 can be considered 2 point something, right? 2 2s are 4, so it will be 2 point something. For now assume it is almost equals to 2, okay. So it will become 10 to the power of minus 34 times 10 to the power of minus 25, so 10 to the power of minus 9, and it will be 1 by 9, 1 by 8, 1 by 8 times 10 to the power of minus 9, okay. Now if you see, all the answers are given in picometers. What is picometers? Picometers means 10 to the power of minus 12, right? So 10 to the power of minus 12, that means we can multiply 1000 by 8 and we can make it 10 to the power of minus 12, okay. This is one of the intelligent way of solving it. So if you solve it, you will get 125. right? So 125, the closest answer is 124. So this will be the correct answer. Simple, don't take too much stress, just solve it step by step, and once you have achieved the answer, check which one is the closest. Okay, so 124 should be the closest. We have not done too much approximation. The approximation is very small, limited. So our answer, so we have done one approximation here, 0.31 we omitted. We have done one more approximation here, 0.34 we have omitted. But overall, all the approximation are not very big. So in this case, square root of 6, we assumed it is square root of 2 point something. So that was also one sort of approximation. That's why the answer should be very close to our calculated value. Now, if you are wondering from where you can get all the information for KCET 2025 physics, including all the chapters, everything, it is available in one place. Okay, KCET 2025 physics 100-day challenge, where all the chapters, all PYQs, including KPL sessions, everything is available. So don't forget to go to this playlist in our channel and bookmark the playlist, so that you can watch from this playlist anytime you want. It will be easier for you to find the chapters, it will be easier for you to find all the videos in that. Okay, so don't miss out on this thing. The playlist is here, you go there, bookmark the playlist like I have done, so you don't miss out on any of the videos that we are doing. Also tomorrow there will be KPL, and it is absolutely free. You don't have to pay a single rupees for that, so don't worry. Join our WhatsApp channel, and the link is given in the description. So if you join our WhatsApp channel, what you can do, you can download the question paper from the channel and solve it. At night I will be giving you the solution for the all questions that we are being asked in tomorrow's paper. So, and if you think we are helping you, don't forget to share with your friends, subscribe to our channel. I will be back with KPL solution tomorrow night, and Monday I will be back with the PYQs of dual nature and radiation chapter. Thank you.